Heavenly Father, we thank you for this day, and I thank you for the students, for this opportunity we have to meet together and study your creation, Lord. I just pray that you be glorified, and we do hear this together. In your name we pray. Amen. All right, so today we're covering how to solve equations using the Gauss-Jordan algorithm. Here's the attendance sheet in there. So I'll explain this in a bit, but first I need to give you the definitions. I just want to put it up there so I don't burn time. Again, so to start with, I need to define for you what is a system of linear equations. All right, so basically we're given constants aij, and let's say b sub I, all right, in some field, and variables. I mean, these aren't really given to us, but x1, x2, all the way up to xn. So this, I'm going to give you a definition here for n linear equations in n unknowns, and here's what it looks like. We have a11 x1 plus a12 x2 plus plus a1n xn is equal to b1, right? So this is the first equation, right? It's a linear equation because the x sub 1s all the way up through x sub n's appear linearly here. And then you got a 21 x1 plus a 22 x2 plus plus a 2n xn is equal to b2. There's the second equation. All right, and this keeps going. We want to look at m of these. M as in money. There are n as in equations here. Excuse me, variables. So a m1 x1 plus a m2 x2 plus plus a mn xn is equal to b sub m. This is a system of m equations in n unknowns. All right. Now, just a little bit more notation while we're at it. We could rewrite this system of equations in a matrix vector format, simply as let's see what it would look like. It would just look like a times x equals to b, or sometimes I might write a times b equals to b. This x is not like written in stone. What would the a would just be the usual thing here. A would be equal to the matrix aij, right? It's an m/n matrix. The b, the so-called inhomogeneous term. So this is an element of f(n)(n). This b would be equal to like b sub I. That would be an element of an m vector. V is x1, x2, xn. All right, so V, that would be an element of Fn in principle. All right, so that's a arbitrary linear equation, a system of linear equations with n variables, and we've got m equations, all right? Furthermore, if v is not equal to 0, right, we say it's an inhomogeneous equation, whereas if v is equal to 0, it's said to be a homogeneous equation. So there's definition. Definition, a v equals to 0 is a homogeneous equation. All right, given the language I just introduced over here. You can, I think there's a couple seats over there. You guys want to go over there?
Thank you.
No problem. No. So homogeneous equations are really special because homogeneous equations always have a very special kind of solution, right? So here's a silly little observation. A times the 0 vector is equal to what? 0, right? Thus, 0, or let me write it this way, v equals to 0 gives a solution to AV equals to 0, all right? The set of all solutions to a system of linear equations is called the solution set. So a homogeneous equation always has a non-empty solution set, because it always has 0 in there, right? On the other hand, if you have a system of equations, you may have no solutions, right? Let's look at an example of that. I'll keep it pretty simple here just for the first few minutes, just to get us grounded. But let's see here. What's an example of a system of equations that has no solutions? How about this? X plus y equals to 1, x plus y equals to 0. What's the solution set to this equation? System of equations. Here we have 2 equations and 2 unknowns, right? By the way, for specific examples, we tend to use x1 equals to x, x2 equals to y, x3 equals to z, because we don't take any particular joy in writing x1, x of 1, x of 2, get away with it. But what would this, if there was a solution, what would it mean? Yeah. Yeah, 1 equals to 0, right? That would not be good. So there's no solution. Now graphically, this is easy to understand too, right? Because this is y is equal to 1 minus x, and y equals to minus x, right? So geometrically, we can even understand this one. It looks like, well, there's a line with slope minus 1 through the origin, line with slope minus 1 through 1, right? There's no intersection point between these lines, so there's no solution. Now, there are other things that can happen, right? Now, we don't have to limit ourselves to, I mean, if you think about the case of 2 equations and 2 unknowns, in the real case, it's easy to see that there are 3 possibilities, right? Either the lines don't intersect, you have no solutions. The line intersect at one point, you've got a unique solution. Or what else can happen? If you have 2 equations, gather to the same line, and then you have how many solutions? Infinitely many. Now, when we work over a field which is not a characteristic 0, like say z mod 3z or something, there don't have to be infinitely many solutions, but there could be other things that happen. We'll see that as well. But here's another example. I'll do one over, let's take the field f equal to z mod, I don't know, let's do 5z, all right? 5 is prime, so this is a field. So what's in here? You've got 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar in our current notation, right? And let's see here. What's the multiplicative inverse of 2? Let's see here. 2 bar times 3 bar was equal to what? 6 bar, which was what in this context?
1 bar.
1 bar, right? So therefore 1 over 2 bar is equal to 3 bar, and vice versa for 3. So the multiplicative inverse of 2 in z mod 5 is 3. How about 4? What happens to 4? 4 times 4 is what? 16, right? But 16 is 1 mod 5. So 4 is its own inverse, multiplicative inverse. So 1 over 4 is equal to 4 itself. Now I'm just reminding you these facts because I want to solve a little equation right here. Let's see here. How about this? What if we have 2 bar times x plus 3 bar times y is equal to 0, and 3 bar times x plus 4 bar times y is equal to 2. Right? So if you look at this equation, system of equations rather, how do we solve it? Well, this one we can use a technique from last week, actually. You can look at this instead as A times the column vector xy equals to 0 bar 2 bar. Right? Is there now some of you have come in late, I'm guessing the snow is coming to us today. Who doesn't have one of these? And that, if you don't mind. almost. We good? Okay. So this is actually kind of an exceptional case because I won't need this Gauss-Jordan algorithm to solve this problem. In this case, A is a 2 by 2 matrix. What is a 2 by 2 matrix? The so-called coefficient matrix in this case. A is equal to what? 2 bar, 3 bar, 3 bar, 4 bar. You get tired of writing these bars if you're actually working a longer calculation. I'm just doing it to emphasize that these aren't conventional numbers, right? These are numbers we calculate, modify them. Now, so, I've forgotten it already. What was it? A is equal to 2, 3, 3, 4. Okay. So what's the inverse to this matrix? See, we have a formula for 2 by 2 inverse, right? So we can actually use that here. I'll remind you that it's 1 over, so we do 1 over, let me just remind you the generic formula. If I have A, B, C, D, the inverse I proved last week works like this. AB minus BC, flip the diagonals, the minuses on the off diagonals. Okay, like so. So if I apply that here, I've got 2 bar times 4 bar, which is 8 bar, minus what? B times 9 bar. And then I've got, let's see here, 4 bar, 2 bar, minus 3 bar, minus 3 bar. Let's see here, so I've got 1 over minus 1 bar, 4 bar, minus 3 bar, minus 3 bar, 2 bar. Let me simplify this a little bit. What is minus 1? Mod 5. 4. Yeah, it's 4, right? So that's actually 1 over 4. And let's see here, I'm going to get rid of the minuses. All right, so that's a 4 bar. Minus 3 is actually what? 2. And so it's just kind of like clock arithmetic, right? You can always talk about time after an hour as opposed to time before an hour. And then 1 over 4 bar is what actually we observed. It's its own reciprocal, right? So this is actually 4 bar, this is 4 bar, 2 bar, 2 bar, 2 bar, multiplied through, what do we get? 8 bar, oh, I'm sorry, 16. 8, 8, 8, which we can simplify to what? 1, 1, 3, 3, 3, 3. There we go. Oh, man. Come on, behave. Save your battery some other time. Okay, so my point then is we have this equation AB equals to B, right? So symbolically we can solve this as what? A inverse AB is equal to A inverse B, right? We can't quite, I mean, we can sort of, you could say we're dividing by the matrix. That's not what we say though. We say we multiply by the multiplicative inverse, right? And A times A inverse is the identity matrix. As I showed you guys last week, the identity matrix times anything is just a thing again, right? So it says that IB is equal to A inverse B, which tells me actually V, which is what I'm looking for, is equal to, let's see here, 1, 3, 3 bar, 3 bar, and then B. Zero bar and 2 bar, there. So what does that work out to? 6 bar and 6 bar, I think. In other words, the solution is 1, 1. Let's see here, we can check that. We can go back to the original problem, which I have lots of blue over here. So if I take x and y both equal to 1, mod 5, what do we get?
5, which equals 0.
Yeah, 2 plus 3 is 5, which is 0. And then 3 plus 4 is 7, which is 2. Now, this is very limiting in some sense, right? Because the only time I have a formula for this 2 by 2, the only way this way of solving a system is going to work is if I actually know a formula for the inverse, right? But we only know this in the 2 by 2 case. So like this method is pretty limited. What's another way we could solve this system? That probably would have been faster. Substitution is a good idea. Let's go back and try that instead. Don't worry, I will eventually get to the Gauss-Jordan algorithm. 2 bar x plus 3 bar y, 3 bar x plus 4 bar y, 0, 2. Okay, so if we want to do substitution, how would you do that? Here's what I do. When I'm faced with something weird like this, I pick something that's kind of a meeting point between the equations. So I multiply the first one, multiply this equation by 3 bar, right? Multiply this one by 2 bar, right? That will make the x's line up. So I'll like 6 bar x plus 9 bar y equals 0. And the second one I'll have 6 bar x plus 8 bar y. I won't even bother to simplify them. 2 times 2 is 4 bar, right? I want the final answer to be in simplified form, but it doesn't hurt you to work with larger numbers and some of the calculations in between. And then what I would do is I would subtract equations, which is just a sneaky way of doing substitution, by the way. So if I subtract the equations, the 6 bar x cancels, right? And you're left with what? Yeah, y bar equals to, now careful, it's not 4, it's minus 4, which is equal to 1. And then you can take that and plug it into either one of these to find x. So I'll plug it into this one. So we get what? We get 3 bar x plus 4 bar times 1, right? Equals 2 bar. So that tells me 3 bar times x is equal to 2 minus 4, which is minus 2, which is 3. Right? And, you know, z mod 5 is a field. So if I've got like 3x is equal to 3, I can cancel the 3's, and I get what? So what's the solution set in this case? Very boring. 1 bar, 1 bar. To singleton, there's the solution set. Now this process of elimination that we just went through, it's nice, right? But what we're doing right now is a little bit ad hoc, right? Like which how did I know to add the equations? What's the process of elimination? How do you do it? What's the system? What's the algorithm for it? And I mean, it depends on who you have this from in high school, I suppose. Maybe you have a specific algorithm, you pick a certain one and you solve for the others, and so forth and so on. This is substitution, right? Well, the Gauss-Jordan algorithm gives us a system, a standard method to solve a system of equations, basically by these kinds of operations, either adding equations, essentially, or multiplying an equation by a non-zero number, or, and here's the kind of weirder thing, you guys tell me that's the first equation and that other one's the second equation. I say, no, that you told me the opposite order. Actually, the first one is the second one and the second one's the first one. Like you can switch the labeling of equations. That's kind of a thing you never really think about doing in problems that you work before you in this course. So these give us the 3 basic row operations. You have a row swap. You have multiplication by a non-zero number, which I mean, so I'm doing the operations on equations here, right? But if you actually look at it, you could just as well have done this with numbers, with a box of numbers, right? I could look at like, I'll tell you what, I'm going to stop working in Z5 here. I'm not sure I want to commit to more. I'm going to cut and run from this at the moment. I'm want to take you to something more familiar to tell you what row operations are. Here, let's run through a simpler, well, not simpler, but a perhaps more interesting example. And we'll follow this algorithm as we do it, okay? So let's see here. How about 1? Let's do 0, 2, 3, 2, 1, 1, 0, and then 1, I don't know, 2, 1, 1. I may regret this. Okay. So here's a matrix. I want to show you how to row reduce this matrix. Now, I guess before I even do that, I should talk about what system of equations would this correspond to. So this would be the coefficient matrix. I'm sorry, I seem to have forgotten to define something for you over here. If you take the matrix and goodness gracious, lost my colors. Well, fine. So this what we're looking at right here would be like the matrix concatenated with the homogeneous term, like that. This is the so-called augmented coefficient matrix. All right, so the augmented coefficient matrix. And so the system that this would correspond to, this is like a shorthand for the system what? X1 plus 2x3 equals to 3. 2x1 plus y1, listen, plus x2 plus x3 equals to something. You guys tell me what it is. Zero. And then we have x1 plus 2x2 plus x3 equals to 1. So this system of equations can be encoded by this augmented coefficient matrix. And then doing row operations on this augmented coefficient matrix would correspond to like multiplying these equations by a non-zero number, or switching their order, or adding one equation to another, all right? So here's the notation. So what I'm gonna do is, now we're at the starting point, and I've called it, this A would actually, A concatenated would be, to be more accurate, okay? So this Gauss-Jordan algorithm, what it does is it takes in a matrix, say n×n matrix, we do row operations to it, and then the output is again an n×n matrix of a very special type. So here's the starting point. What we do is we find the leftmost non-zero, non-pivot column, and swap rows until the topmost non-pivot row is a non-zero entry. Now that's just fancy for saying, look at your matrix, find the first column which is non-zero, right? This is the starting point, so it's this one, and make the topmost position in that column that's not already a pivot column non-zero. Well, there are no pivot columns before, right? So that means that the first pivot is up here. Okay. If you had a perverse matrix where the first column was all zeros, you'd have to go on to the second column, right? We almost never look at that example. So there's your first pivot position. Now, the forward pass, which we then do, is we subtract copies of the first row to clear out the zero below that pivot position. So let's see here. How can I get rid of this 2? I do row 2 minus twice row 1. Right? Now, row 1 is unaltered, so I just write it again. 1, 0, 2, 3. Now then what? So minus twice row 1, so I get 0. 1 minus twice 0 is still 1. 1 minus twice 2 is what? Minus 3, right? And let's see here. 0 minus twice 3 is minus 6. Do you guys agree? Now, we can actually do 2 row operations at once to save ourselves some writing. So next I'll do row 3 minus row 1, right? I can just do that. the ones cancel, right? So I get a 0. 2 minus 0 is 2. 1 minus 2 is what? Minus 1, right? And then 1 minus 3 is minus 2. Okay, at this point, I have done this step. I have added or subtracted multiples of the pivot row, clear out all non-zero entries below the pivot in the pivot column. We're now to that point. Okay, and then so I go back up, follow the arrow back up here, and I go, okay, now I gotta find the next non-zero column, right? Which would be what? Obviously this one, right? And the next pivot position is going to be this, right? Because I've already used the top row already has a pivot, so I can't put another. There's only one pivot in each row. A row can only have one pivot at most. So that's my next pivot position. Then, what do I got to do? I have to add or subtract multiples of the pivot row to clear out non-zero entries below the pivot position. So what's next?
R3 minus 2R2.
R3 minus 2R2, which is what you meant. Maybe what you said. Sometimes I hear wrong things and it's just mine. I guess it's, I don't know what it is. You can decide what it is. I don't believe in psychology is a discipline, but I can't answer that question. Let's see here, minus 3, minus 6. All I know is Jeremiah 17:9 tells us that the heart is desperately above all things, and you can know it. So my hope for coming up with a meaningful theory of philosophy of psychology is somewhat dim. So 2, so that's 0. And what do we got down here? 5. Oh, I'm sorry. Yeah, what is it? I think I lost track. Oh, 5. Yeah, I'll buy that. And minus 2 plus 12, right? So 10. It's good? You're like, you mean to tell me if I make a mistake at one of the early steps, it makes the whole thing wrong? Yeah, it does. You have to be careful. These require practice. You shouldn't try to do them when you're sleepy. Now, at this point, some people would say that we're done with the forward pass. Other people would insist that I rescale this last one to have length 1, all right? But basically, that's the forward pass. What we do is we identify the pivot positions, and we make everything 0 below the pivot positions. See these zeros like that. Now, my next move, just for the sake of making things nice, is row 3 divided by 5. So I got 1, 0, 2, 3, 0, 1, minus 3, minus 6, 0, 0, 1, 2. Hey, you know, I just made up these numbers. This is very lucky. Usually they're fractions. Okay, now we have earned the right to go over here to the backwards pass. Now, if you have a calculator, the oh, come on. The row echelon form, the REF, or the fraction. Yes, your ice climbing is very fascinating, but okay, matrix back. Then, okay, fine. All right, there we go. So the REF is not unique. Like if you pick the pivot, there could be some ambiguity in the selection of the pivot position, and that ambiguity can end up giving you different upper triangular. Well, this is not quite upper triangular, but sort of. Well, you see what I'm saying. I mean, it's kind of upper triangular, but it's not a square matrix. I can't say it's upper triangular, right? But it's like upper triangular. This is echelon. So echelon is just basically what is it? It's French for stairs, I think. So it's kind of like a stair, you know. But again, 0 is below the pivots, and you can have non-zero stuff above. Now the backwards pass, what we do is we go from right to left, the rightmost pivot, and then we make the things above it become 0. All right, so my next move, and do it in thread. Actually, what are my next 2 moves? So this is row 2. So my notation, guys, is I write the row which is modified first. Notice that row 2 is modified, row 3 is modified, row 3 is modified. Whichever row is modified gets written first. So here row 2 is being modified. Row 2 plus 3, row 3. And then row 1 minus 2, row 3. So that gives me 1, 0, 0, 0, 1, 0, 0, 0, 1. The 2 is unchanged. So row 2 plus 3, row 3 would be 0. Minus 6 plus 6, right? And then, let's see here, minus 2 times 2 is 4. 3 minus 4 is minus 1? Wow. That is really lucky. So, all of these weird things we've done with row operations correspond to what? Multiplying an equation by a non-zero number. Or adding one equation or subtracting one equation from another, pretty much, right? So that none of those operations change the solution set. What that means is that this system of equations I started with, right, is entirely equivalent to this system of equations that I've ended with. By the way, this is the so-called reduced row echelon form of the augmented coefficient matrix, A, candidate with B. This is a unique output. The process of doing this backwards pass removes any ambiguity in the REF. You can prove that that's a unique outcome for a given matrix. The REF, the reduced row echelon form is a unique output. I'm not going to prove that in here, but the proof can be found in like appendix something of Inzel, Spence, and Friedberg's undergraduate linear algebra book. It's very, very exciting. Like, it's very exciting proof. I'll let you read it. But so just to be clear, this, on the other hand, is a system of equations, a very boring system of equations. The first row is x equals to minus 1. The second one is y equals to 0. The third one is z equals to 2. Now this system of equations is very easy to solve. Right? I mean, okay, so you can see that the solution here is unique and is in fact what? So there you go, there's a solution set. Now, any questions?
You used x1, x2, and x3 in your
Oh,
original
I'm
equation.
sorry, that's a good point. I, generically speaking, said x1 equals to x, x2 equals to y, and x3 equals to z if I have a low, my problem has low enough dimensions that I can get away with not writing subscripts. So, I was writing subscripts for pedagogical reasons over here, and then I have ruined that over here. Thank you for your question. It's helpful. You're like, I didn't really follow all the steps you were making. You're going too fast. I don't get it. Well, that's probably the case. Sorry about that. But not too sorry, because you live in an age where there's this thing called the internet. And, well, check it out. So, like, here's a different problem. There's a link to this on the website. It is through a professor, I think at Nbyn, if I remember right. I just emailed him to get permission. Again, he used just I forget to ask him permission. I'm always using this website. Oh, come on. Hey, that's not cool. Okay, great. Good job. Haha. Take that website. Not the boss of us. All right, so here's just an example I put in. Now this would be like what? Now some of you may have been taught the Gauss-Jordan algorithm in high school, right? Some of you may even remember it. Others of you may have never seen it again before. And I mean, we all come from different backgrounds. But anyway, you need to learn it now. So whoever you are. Now, I'm not okay, so this is the algorithm I just went through here more or less. Technically speaking, I mean, if you're just after solving the system, you can stop here and do back substitution. That's faster, right? But I need this construction for the sake of uniqueness and arguments we make in here. That's why I'm going through the whole rigmarole. If you're just after the sole goal of calculating the solution set, you can get away with less sometimes, right? What's the optimal algorithm for all possible situations? I don't know. That's like, it's like asking, how should you approach a dating relationship? I mean, there's as many approaches as there are people. Every equation has its own identity. You have to treat them differently. Same for people as equations. But this right here would be something like x1. I don't know. Even now you can find new tricks. No matter how long you study this, there's always some new trick to learn about how to solve a particular subclass of certain kinds of equations. So the generic Gauss-Jordan algorithm may not be the best for a given special problem. Like, how about this problem? If you're given this system of equations, the one that's exploding, you don't need an algorithm. You just need common sense. It's already solved. x1 plus x2 plus 2x2, x3 rather, equals what? Equals to 0. So I'm interpreting this matrix at the moment as a system of how many equations? 3 equations. And how many unknowns? 5 unknowns. Oh, 4 unknowns, yeah, sorry. Then 8. All right, so, I mean, I hope you save some money to register for this website. Well, not really, it's free. So there it is, and it shows you step by glorious step, the row reduction here. Add -1 times the first row to the second row. As you can see, it's color-coded in red, modification. And then add -2 times the first row to the third row. As you can see, he has now cleared out the first pivot column below the pivot position, which is the other one, right? Then he moves on to the second pivot, right? And he's going to add 7 times the second row to the third row to clear out that one. And then this is going to be the third pivot, right? And there's fractions as usual. And now he's clearing out, he's doing the backwards pass now. And almost done. And now we're back to the second pivot. We got to clear out that 2 up there. And there you have it. The reduced row echelon form. Reduced row echelon form of the matrix 1, 2, 3, 4, 5, 1, 1, 2, 0, 0, 2, -3, 4, -7, 8 is equal to, what's it equal to? 1, 0, 0, 0. I'm doing the first 3 columns because I know what those are. Then the other ones I have to think. -47/5. Interesting. And then what? -58/5. Then what?
-7/5.
7/5.
-8/5.
-8/5.
27/5.
27/5.
Yes. And 33/5.
33. Now, you guys have some work to do so that you're proficient in doing this in a reasonable time frame, right? If it takes you 30 minutes to do this, then you're going to have a hard time on the next quiz. You need to do enough of these so that you get a little bit fast at it. That's part of the next homework. It will help you get up to speed. Of course, you should check yourself with this website or some other reasonable technology, right? What does this say, though? This says that x1 -47/5 x4 is equal to -58/5, right? This second row says that x2 -7/5 x4 is equal to -8/5. And this third one says that x3 plus 27 over 5 times x4 is equal to 33 over 5. But so wait a minute, what's the solution? Well, this is 3 equations in 4 variables. There won't be a unique solution if there is one at all. Is there a solution here?
Yeah.
Sure, take x4 equals to 0. You can see that the solution is, minus 58 over 5, comma, minus 8 over 5, 33 over 5, comma, 0. But more generically, the solution set has the following form. So what we got? We've got minus 58 over 5 plus 47 over 5 times x4, comma, minus 8 over 5 plus 7 over 5 x4, comma, 33 over 5 minus, that's what I'm doing, guys. I'm solving for x1, x2, and x3 respective. And I'm writing them in terms of x4. See, x4 is going to serve as what's known as a parameter or a free variable in the solution set. The solution set in this case is infinite. I mean, geometrically, the solution set's a line. Yes, sir.
Wouldn't you need to have a 4th term in the solution set that was just x4?
Don't I have that?
I don't think so.
Oh, I didn't write it. I'm sorry. I was, I guess it was typesetting. I was hoping. I wanted to squeeze it out. There's no good excuse for it. Follow me. Yeah. Yeah. I am not perfect. I make mistakes. Yes, it's true. There's one. But yeah, there should be 4 things. 1, 2, 3, 4. So in this case, x1, x2, and x3 are the pivot variables, right? And I've written them in terms of the non-pivotal variable, which is x4. So the non-pivotal variable will be a parameter in the solution set. And this is true for other expressions. Okay. Now we can do this algorithm that I showed you. We can do it over any field. We can do it over reals. We can do it over. Okay, I heard something. Right. Z5. I mean Z mod of prime. This not so much help to you in the finite field case, right? That you're just going to have to kind of figure out for yourselves. I will. I have an example over Z11 that I'll try to post online later. I mean, I don't want to. It'll take me half hour class time to go through it. So I'll go through it and post a video for you guys to look at if you want. So any questions about this? There are lots of questions they ask, right? Yep.
How do you know like when to stop? Because you keep going, I feel like.
Well, let's see here. Let's try for something else. How about do like 8 columns? And wait a minute, what am I doing? That's confirmed. Columns. You guys give me some numbers.
8.
Shout out the numbers are 1. Okay.
6.
7.
7.
2 or 3.
7.
Maybe they're only that. All right, fine. The rest are 1s. I would expect in a room full of math majors, someone to shout out pi or e or something.
I was going to say tau.
You're going to say tau? Get out of here. It's here, no.
Whoa.
So, Christina, that's your question, right?
Yeah.
So how do you know when to stop? When you run out of non-zero columns where you can't put another pivot position. I might be able to see that in this example. Curses. Look at this. Sorry. Second we try for one where that actually happens.
Val.
That's not gonna work.
6.28.
Well, one silly example of that, Christina, actually would be the zero matrix. What happens when you run the Gauss-Jordan elimination on the zero matrix? You feed it in there and it looks for a non-zero column and it goes, ah, there's no non-zero column, I'm done. So there's an example. The zero matrix. Not very exciting, but true. The matrix, all of ones. So this one's just going to have one pivot position. Because after we clear out below that first pivot, we're just going to have one row, non-zero row. And that's it. So you don't have to have anything can happen to the right of a pivot position. Like that's totally open. Anything can happen. But it has to be zero below and above. This particular example is the case we had the same equation repeated 5 times. Right? There's really only one equation. And in this one, if I was to write the solution set, there would be 3 parameters. Assuming that this represents just a system of equations. Here, let's go back and try something slightly different. 3. So all I did was put a 3 there, right? So I can tell you what's going to happen. Where that 3 is, there's going to be a pivot position right here. That's what's going to end up happening. So again, once the reduction is done, above the pivot position 0, below the pivot position 0, there's no more pivots defined here because we have no more non-zero. We have no more non-zero column where there. Like, okay, here's a non-zero column. Here's a non-zero column, right? But you can't put a pivot position below where there's already pivots. Now, my wording in the boxes may not be quite right. I mean, I tried my best to make a flow chart. First of all, I tried to Google it and find a decent flow chart online. I could not find it. What I have in the notes right now is just like a list of demands that I got from Inzel, Spence, and Freeberg's book, which is good. It's a very careful algorithmic book. This idea of doing the forward pass and the backwards pass is not in all books. And it leads you to something called the LU decomposition. I don't cover that in here, ironically enough. But doing it in this way does lead to other matrix theoretic things that I don't cover. What would happen if I put like a 8 here? There'll be 3 pivots. Like, you might wonder, how do I know that? There's a lot going on with the algorithm. How do I know that there are going to be 3 pivots? Well, I have another understanding of what it means, what this reduced row echelon form means to the matrix in terms of what's called linear independence of the columns. Right? So something else we'll be explaining this week as we go on, and then you'll understand why I knew immediately that there had to be a pivot position in that last column once I put that 8 there to start with. But you see again, 0 is above and below, 0 is above and below. Right? Now, if this corresponded to a system of equations, right? If we had 4 variables and 5 equations, this would be an inconsistent system because this column, this row right here would say what? x1 plus x2 plus x3 plus x4. And 0x1 plus 0x2 plus 0x3 plus 0x4 equals to 1, which would be troubling. So we learned lots of new things as we go on in math, but 0 can never be 1. Can't get around it. Let me just show you a few fun facts about the Gaussian elimination before we leave today. Well, I got this silly projector open. There's so I have actually oh come on. Sorry, it's awful. I will eventually learn how to look at a PDF on this thing this year. Some semester. So I have careful definitions of row addition, row scaling, row exchange in the notes. I won't waste your time writing those on the board. I came up with these formulas for your notes. I think it's fun. Here's an example. there's more examples. This is a composite row operation. Technically, it's not an elementary row operation. Elementary row operations are row swap, row addition, row scaling. So you can put them together to do a composite row operation. More interesting, here's the algorithm, which I made into a flowchart for you guys. Some examples. These are the ones I'll post videos for, because I owe you some more examples over like a finite field. This is more important. Proposition 2.5.26 basically tells us that if we do the row reduction on a matrix A, right, and then we glue columns to the left, to the right of A, that are 0, nothing happens. As you do row operations on a column of zeros, what happens? You switch 0 with 0, you multiply 0 by a non-zero number, you add 0 to 0, it's 0. So if I calculate the reduced row echelon form of A with 0 slapped on, I still get the same thing with a 0 slapped on. That's a nice thing to know. What that means, by the way, is that if you're doing the row reduction on a homogeneous system, you don't really need to write down the B part. You can just omit it. Instead of doing row reduction on A concatenated with B, you can just do row reduction on A and figure out the solution set. But you have to keep in mind what you're doing, right? It's unique. There's a lot more solution set examples in here. I'd encourage you to read them to come to terms with how the solution set is constructed from the row reduction. This theorem is only true over characteristic 0 for the reals or the complexes. If we're in a finite field, I think what we're going to find is if there's not a unique solution, suppose you're working over like Z3, you might have a solution set where you have 3 things, or 9 things, or 27 things, or something like that, if you have the non-unique case. I'll include that in the example I post, hopefully. And then so finally tomorrow we'll pick up with how to solve multiple systems at once, and that will lead us to study elementary matrices, and then ultimately find formula. One of our ultimate things is to go back and find a formula for the inverse matrix, or beyond the 2 by 2 case, like your matrix cases before. Anyway, thanks, guys.